Typically, we would be presenting either a technology, a product, or features of a product. Here, we want to sort of open up the doors to, let's say, my part of the FRAMOS sort of family, and that is to talk about how we go about helping customers take what is either a new or definitely a complex product and turning, as in an image sensor, and integrating that into a device to create a full system. So just to go through, we're going to have a quick introduction. Very clearly, I want to actually classify what bugs are, just to try and put them into different sections, because each sort of classification of bug has a different approach to it. You know, do you break out the oscilloscope? Do you go back to the reference manual, etc.? We're going to talk about a debug approach. It does, you know, it follows normal sort of best practices in terms of looking at hardware. But at the end of the day, it's all focusing around any kind of evidence that you can get out of your system will help you plan your next step. And then I have lots of examples. And hopefully this short format sort of presentation will allow you to get an understanding for the ideas and the way of thinking, if not actually a direct answer to any specific problem that you have. And because on that vein, this is a very big subject. How to debug a particular device is very much defined by what that bug is and how that bug looks. If you consider the wide variety that these imaging devices sort of manifest themselves in, they can be small, battery powered, lightweight. They could have to live inside a very harsh environment. There are as many imaging sensor and imaging system designs as there are the actual use cases and the decision on how to actually build something, either for cost or for reliability, or generally a mix of the two. There's also a wide variety of choices. There are so many different ISPs, FPGAs, etc., that you can bolt onto the back of these image sensors. And that is that choice and how you want to do it is obviously slightly governed by the image sensor you're trying to integrate, but it also is heavily governed by what you want to do with the data at the end of that passage. The other thing to mention is, not only do you have this wide variety, but even if everyone had the same exact hardware, the actual way that you're running that system, or the way that you go about programming it, that system, can easily introduce complexities and difficulties. And that leads us to this vast configuration space. So if you look at the imaging device as a whole, you would actually have all the configuration for your image sensor, which is what we're going to talk about primarily, but then you also have the rest of the system to be configured. Maybe there's a host PC, maybe there's some cloud surface that's connecting to your camera, etc., etc. So the idea of what is an imaging device and how to find a bug that's inside that its day-to-day operation is very, very difficult. And something that's actually more about the hardware and the sort of low register level access is that any error can manifest in any form. What that means is, if you have a single register value that's wrong, that could do no perceivable damage to your normal operating image. So you can't see any effect for this incorrect register. But as soon as you change to a different mode, it completely goes black, or there's no data output. So it's very important to understand that the smallest of issues can cascade in combination with the complexity to make a system that doesn't work. So how do we sort of look at this? If everyone has a different piece of hardware, they have a different use case, they have a different image sensor, although from the hundreds that we already offer, how do we break it down? So typically we would break it down to the image sensor, obviously. So that is a single device. It has to have other supporting hardware, as in it doesn't work on its own. It needs electricity. It needs to have control. It needs to have data to it. So we effectively we consider that one on its own. We then can say that the next kind of large section of that would be the host device. So this is something that does the data consumption. It will do some processing perhaps and pass it out, but it also does the control and configuration. And next, you need to glue it all together. You need to get you have to get the bits from one part to another. So therefore, we're going to have PCB and all of the hardware that surrounds that type of thing, as well as power supplies. You need to have something to give the system's bulk power. And in fact, this power supply one is quite a big subject in itself. So what is a bug? We define what the imaging system is. For me, something I decided seemed quite reasonable was the root causes of the differences between the expected and the observed behavior. The reason that expected and observed are highlighted is because expectations is what I also considered to be a bug, and the way that we observe the data coming out of the sensor, or how we validate that we have or have not got a bug, can also be the bug in itself. So, for example, if you're complaining about resolution not very good, but you're looking at a compressed image over a JPEG stream, is definitely look at the compression to see if that is actually causing the loss of fidelity to your raw image, rather than tweaking the sensor continuously. Because if you're compressing something heavily, there's no way you're going to be able to recover the image quality through changing the settings on the sensor. And the other part is to squash that bug, you need to know where to stamp. And again, leaning towards this expected and observed, or if to stamp at all. This is a very key point. That a lot of wasted time, wasted is maybe a bit too harsh, but a lot of spinning of wheels occurs when we're trying to classify, when we're chasing down sort of bugs which are not actually there. Okay, so this is my wonderful representation of an image sensor. And I want to just classify, so we had the expected and the observational bugs. They're not actually to do with our product, they're to do with how humans are, really. So what we can now look at is, with the image sensor, we have the first one, which is a configuration bug. So the image sensors are highly complex devices. They are a combination of analog systems as well as logical systems. There are high speed, high bandwidth, highly complex data interfaces. There are some strict timing regimes, and those strict timing regimes occur in the logical process and flow, as well as they occur within sort of longer term, but still accurate requirements for analog timing. And so this kind of mix is what gives us that level of complexity. Just to sort of illustrate that, this is a representation of just what you would do with a line pulse. So for example, you give a line pulse to an image sensor to tell it to change lines. That actually drives a huge number of things, including this very innocuous looking little process here called analog activity. But the key is that multiple register values are used by multiple small sections of logic within the image sensor, a state machine, if you will. And those all have to combine and do this and all work together at the output. So it's similar to having multiple chains of actual physical cogs. They all need to mesh together correctly. When you turn the main one, let's say, which would be in this terms the input clock, all of the larger and smaller ones have to work to create that correct output. Any error will produce an incorrect output. Okay. One of the sort of key points I want to make here is the configuration bug, which is this register map right here. And this is the way that we interact with all of this. We program it, we set it up, we change these timers. This is the complexity. And this is also where 90% of all issues are actually traced to be. Finding hardware bugs is quite easy, and we'll talk about that. Well, it's easier, and we'll talk about that shortly. But this register here, although I haven't put too much highlight on it, the numbers that go in here are the program. They are defining the hardware states for the image sensor. These are where it could be. For example, if we accidentally change this O3 to an OB, which is a valid hex value, the system would work completely differently. Half of the sensor would be incorrectly mapped to the rest. So although if we sort of go back one stage and we think, oh, this is a very simplistic approach, we just need to get this and get this right, it is also quite difficult. There are 300 different typical registers that you need to set just to get the system operating, and that's not during configuration. The next one. Then we have hardware bugs. So these are basically extra hardware or missing hardware or hardware in the wrong place, for lack of a better expression. So the first one we have is sort of design errors. Typically, if you have a device that could have up to 600 pins, each of those pins need to be treated very, very well and accurately, either as a digital device or an analog device. We can have this, we can have just the simplicity of or the vastness of the task causes there to be an issue. You know, humans are not 100% perfect. This is why we have prototype stages. But having that design error and then trying to find it is part of what we aim to do. The other thing is within the design errors is sort of design intent. Especially when you're moving from, let's say, a prototype into a mass production device, we're changing a number of things. So we're making it smaller, we're meeting the new physical sizes. So we might have to do things like remove certain passives or move those passives away. And because we've done that, we would then have the system may operate in a different fashion. So, for example, removing this or forgetting to have this populated either by the CM or something, the absence of this device could make the system not work. This could be a critical piece, for example, the analog power supply that actually provides the power to reset each pixel. It could be something as along the same lines, but it could just affect the noise. So the whole system works perfectly, except the images just don't look as good as your prototype or don't look as good as the evaluation kit that you originally had in place. So it's key, it's something to know about a bug is its manifestation, as I said, could be anything. Those are not just it works, it doesn't work, but those are every 10,000th image. I'm not seeing the image that I expect, either in terms of quality, accuracy of timing of it, the event it's capturing, etc. So bear in mind when you think of the configuration and the hardware, we can affect the whole scope of what anyone can say that is not as I anticipated. And then we have manufacturing errors. So again, these are physical issues. Typically, there are things like additional solder, so shorts are what we sort of typically deal with, where during their manufacturing process, we've broken the idea or the concept that was in the design. So if the design's perfectly fine, but the CM uses the wrong process when backfilling vias or creating something within the PCB mask, then you will have an issue that you have to then debug, because everything checks out in a schematic, everything checks out across the whole paperwork side of things. It's just physically we now have a bug that we have to track down. So moving forward from there, so we have this expectation, observation, hardware and configuration, classification of the bugs. What we can now say is, well, if we get rid of those two and we have this just hardware or configuration bug, i.e. there is a real bug that really needs to be tracked down, where do we start? For me, I always like to start at the fundamentals, the most fundamentals. So, for example, the most fundamental toy or tool, I should say, I have in here is my VM. So we have continuity checking as well as sort of voltage checking before we move up to things like oscilloscopes and logic analyzers. So if we start at this sort of lower level and build upon that, we're able to make a decision of, actually, let's go back and say it this way. We can make a decision as we go through this process. Are we looking at an error, a fundamental error where we're not receiving a frame at all, or we could be receiving a frame, but the FPGA, for example, is not actually processing it. So locating it, because again, this is a vision system, and because we have the image sensor and all this ancillary hardware just to make it working, we can't view through, we have to view our bug through that other hardware, where there could also be a bug. So where to start? We can roughly classify this into two stages. So typically people who approach, or customers approach me, first of all, they're good engineers and everything's sort of working pretty well. And but there's an issue and we need to isolate that. So we have issues where we have no image at all, or should I say no data that resembles image data, or we have something that does resemble image data. So on the right-hand side, we have a data structure. For most Sony image sensors, this is sort of bounded by sync code. So we have this continuous bit stream we have this continuous stream of data over our connection, and we can actually, using that, we can find out where's pixel 1, 2, 3, etc. So this would be, if we had a fully working system and only a partially working sensor, this is the type of image that we would see. So let's say that we have no data structure. So this is starting at that very bottom rung. So we can say the first thing we need to do with power. Without power, nothing will work, and we can't check any other stages. So the idea for these image sensors is to check that we have all the different power rails available. So this would be the analog power rail for the logic, the data comms, let's call it the communication power, as well as the interface power. So these are the typical three. Please note that some sensors have up to 15 power supplies, 6 or 7 different ones are for analog and etc. So the complex and very large devices have that. Now, these 3 extra lines at the top here are also critical. These are representative pin strapping. So when you turn on these sensors, at a certain time you turn on the power supply, you need to have a particular pin held high or low. If that pin is held correctly, then the system will communicate as you expect. Otherwise, you might be trying to look at high-speed data when you thought you had selected a low-speed data interface. Many devices have multiple interface, both speeds and actual hardware options in interface styles, I should say. And similar with I2C or SPI communication. If you don't have the pin strapping right, then you can't communicate to it. But once you have that done, we can now look at our comms and configuration and say, right, we've got power, we've verified that power, simple as the VM here. We can now see if we can communicate to that device. Simply saying hello to the address for the image sensor. There's a typical address. Pin strapping, by the way, can also affect that address. You can have multiple different addresses for a particular sensor. So you need to know that your configuration is mapping through to your expected communication. That communication is typically a single little link. And once you have established that communication and verified it, such as reading back a known value out of the sensor, and then writing and reading back a value from a known register that you have read-write access to, you can now say, I can now apply a configuration. And then you can push that configuration into your sensor. Once that's into your sensor, if it's a known good configuration, typically that could be available from something like an EDB kit, where you'd have it, or you just built it from the raw data. So this is one of the devices I typically play with all the time. By the way, this is something I have to break to match your device that doesn't work yet, and that's the kind of communication barriers that we have to try to overcome. But if we have a known good configuration going into that sensor, we can then look at various aspects, connections to our FPGA to see if the data is there. That doesn't mean we have to look at an image level. We don't have to say, hey, I can't see an image. What you can do is you can say, I'm going to set a certain pattern of data onto my data lines, and I'm also going to look at my clock line, and then I'm going to decide whether I can see it or not. So typically, I don't have access to a very fast logic analyzer, or even better yet, I'd love to have an even faster oscilloscope. But what we do have is within FPGAs and FPGA designs, we typically have the ability to do some capture inside and dump that to a main PC. This is the Xilinx Xilinx system. So this is an ILA out of a Xilinx chip scope. And what we would do is we would actually put known data onto that system and then just say, hey, look, it should go 1, 2, 3, 4, etc. So we can actually have a look at the data as it comes in to our FPGA and then verify that it matches what we expect from the output. So let's say we have done that. We've gone through those stages. We've found that there was a bug, let's say, in our hardware, and it's been corrected. But now we're getting data coming through from our new configuration that we copy pasted from an EDB. We now have image data that looks like this. Typically, we need to now know is this an observation error, or is this a practical issue with our register set? What we can do then, in this case, is we can send a known test pattern. These test patterns are generated sort of in the last stage of the image sensor, just before the actual the transceiver or the transmitter hardware. The logic for that has a little state machine that can run that enables this test pattern. So it doesn't matter what the rest of the sensor is doing in terms of the small fine detail. The output data from those transmitters will have a known format. So in this case, we have color bars and we have a grayscale. So what this means is I can tell you for every line what the value should be for a particular pixel. And so therefore I know how using the data sheet, I know which pixel should be on which data connection, and therefore I can then see if there's an issue with a particular data connection. Potentially swapped polarity is a very big one that we see, or maybe there's this one is just not giving any data. It's giving either an error, but more typically it's just giving all black or all one, and all zeros or all ones. And so what we would then end up seeing is the like a vertical stripe pattern on top of this. So when we know what we should see, we can then tell if we're looking at it with, in the correct way. Just very quickly, just for those who may not know, we're always dealing with single values per pixel in terms of grayscale values per pixel. A Bayer color image is still just a pattern of single valued pixels, so where we have red, green, and blue, and we just use an average of all of those to create multiple values per pixel location. So this color is still a monochrome image. I've just displayed it in this way. So once we've got this test pattern in, we know what the data should look like. And then we can say, right, well, our original test where we just threw the entire configuration at this didn't work. We've now proven all of these stages. We've got a hardware proof, communication proof. We have the test pattern traveling through quite nicely. What we need to do now is have a look at the how to, we need to now iterate on top of that working model to get to where we need to be. And that is a very valid way to do this in a very safe way as well. So what we would do is we'd actually, like we said before, enable that test pattern. We can then confirm our pipeline is transmitting that as we expect. That's great news. Check our configuration, because we're going to change our configuration changes, register changes, change those, test it. Did it work? Yes, no. And effectively, if you just concentrate on these small elemental features and then build them up, you will then find that any bug that you had would come out because you are doing you're checking various stages. So let's say you wanted to do a bin system where you reduce the resolution but increase the sensitivity of a particular sensor, and you also want to have external slave control, for example. And at a custom resolution. The first thing you would do is get that test pattern working, and then you would convert the fundamental sides of it. So in this case, we changed the bit depth because this, the kit we got with our AVB had a really good 12-bit set, but it didn't have an 8-bit set. By the way, they do. So this is slightly theoretical. But what we can do now is move through this. We can apply just the bit depth and then make sure it works. And this type of loop here allows us to both change small parts of our image sensor configuration, make sure it's outputting the right data, and then validate our pipeline. Because again, if we can't see it, we can't necessarily believe it. So as we sort of move through, we would then do something like a resolution change. Okay, we now know the bit depth, so the data format, the fundamental data format is good. Now let's have a look at the actual overall data structure, and let's make sure we can get the right resolution, and that is then compatible for our system. We could then say, well, now that all works, that's great using internal timing, which is generally simpler to get going. Now we need to get that to work with the external timing model, where we're driving it externally, because we may have multiple sensors that are all operating at the same time, or we may have multiple other devices that we need to know the timing thereof. Sensors, by the way, are typically the master of a system if there's only one image sensor. If they're not, one will be a slave and one will be a master, just because of the simplicity of that. As you move into sort of other types of cameras, especially like broadcast and studio, then there's something else that's in charge of all the timing. But in most cases with a single image sensor, master mode is more than sufficient. Okay, so with this kind of little approach, we sort of need to identify a few errors that we see. So we have this foundation, this ability to work up through our sort of hardware, through our configuration, until we get to a base operating mode, and then we want to move into a configuration. But are there any shortcuts to this? Because for something like a polarity changed LVDS connection, sometimes it looks, an image can look really quite good, or it looks very much like you could just be seeing the limit of the sensor's capability in terms of image quality or the noise it has at low light. How do you know that you're seeing this real stuff? And one thing to do is to learn to sort of, if you can, recognize the image types. This is where the experience that I've gained throughout my years with FRAMOS, this is where being able to see images and just be familiar with them because you've worked with them so long, it becomes a little bit like being able to see a register set through the image damage. In this case, we have a data stride error. Now, if you look at this, you can probably recognize there's some shapes here. There's a Macbeth chart, if you're familiar with the color checker at the bottom. And what we're able to do, what we're able to look at in this image is, first of all, there is some strange patterning here. That's actually a moire from, this is a scaled Bayer pattern, but that's not the key. The key is that all the values are off. Everything's wrong. This is this. So this is an aerosol with a white cap. So where it's white, it's now completely black. What's going on? The next time we turn the system on and looked at it, it's now, you can see that it's got the cap is now not black, but it's not exactly white at the moment. And what this is actually a data stride error. So as we've said, when I was talking about the bit depth setting, if we say this is 12 bits, you literally have 12 bits, which is your pixel value, and then you'll have another one, which is your 12 bits. If you have 8 bits, it'll be 8 bits, and then the next 8 bits will be the next pixel. The key is knowing that that you are in the correct bit depth mode, so your FPGA is intercepting and observing this data correctly, but you also need to make sure that you actually start in the right place. You're not like taking the half of one pixel and half of the next pixel and calling that pixel number 1. And that's what a data stride error would look like. Color. Both of these images look quite nice. So in this case, I'd actually say the image sensor is absolutely performing, absolutely pretty well. But which one is it? Do I have an orange background or do I have a blue background? Those familiar with the color checker would actually see that this one here is the real color image, and this is the real one and this is the standard Windows desktop. I don't have it to hand, but I also have, this is an orange screwdriver handle, this strange blue thing, and this is a keyboard light, which is definitely blue and not orange. This is a very easy mistake to make, and it also happens a lot in commissioning where there's a lot of additional modes, and that's because the image sensor, depending on which image sensor you're using and depending on how you read it out, as you change resolution, as you drop pixels from above and below and left to right, or read it upside down or back to front, you will end up getting your pixel array, your Bayer pixel array. The first pixel will be blue in one instance and red in another, and therefore when you apply your debayering, you will not actually get the colors you're anticipating. You'll get some crazy looking colors. And so these are the two sane ones where we swap red and blue. If you swap green and red or green and blue, you'll generally get really crazy magenta or very teal looking images. So that's a good hint that you've got the wrong debayering process. The other thing is, with color, that the issues don't have to be so gross, they can also be subtle. If you have a look at this image, I'm not sure how well the resolution comes through, but on the left-hand side, and we have a standard image. On the right-hand side, we actually have an image that has some additional processing done to it. That additional processing is good and bad in this case. So the things that were applied were a CCM, a color correction matrix. This is something needed to take the true data from the pixel, and when you debayer it, knowing the actual behavior of that system, knowing the behavior of those pixels and the color filters within those pixels allows us to make sure we find the truest color representation possible. But you also notice, I don't know, unfortunately I can't zoom in on this particular slide, but there's also a crazed pattern. There's an artificial sharpness that's been applied to this image, which actually, if you were to zoom in on these, you might end up liking what looks nicer on the left than on the right, just because that artificial sharpening adds texture into our color patches. So getting to know about the process flow that you have is very key. One of the main issues that we see when it comes to when we can see an image is timing. Is black images. And this is generally based on the internal timing. As I said before, we have the sensor has both logical and analog sections to it. The analog sections need, let's say, a millisecond to achieve something, whereas the logic side needs a certain number of ticks or clocks. And if you're going to read out something from the analog side and then you change your input clock, for example, you need to therefore change the number of counts it needs to wait for that to be available. The typical one with the ADC. So a normal sensor has a column ADC, which means every single sort of column of pixels has a digitizer at the bottom that will turn that analog information into digital, and we can read it. But if we don't give it enough time to actually attach to that signal and then digitize it and make it available on its memory output, it won't provide us anything useful at all. In fact, it'll provide us basically a black image. And what that black image is just sort of some residual behavior, some undescribed behavior of that electronics at a fundamental level. If we enhance that, we can then see it will look something like this, and it is pretty much not a good thing. There are many different ways to get black images. They can be truly black, and if they're truly black, we would have a look at the data signaling electrical levels. If they're noisy black, so they look like a pixel in the dark, we'd have a look at the correct timing to make sure we are really exposing those pixels and we haven't got a register error. We could also have pixels where it seems to obey perfectly, but it's always all white or it's always all black, and then we'd have a look at the analog side of the connections to make sure we have sufficient data. Also, sections of the image could be black, and they could lead to other power supply ripple issues. As you're going through, or as we're going through looking at various images that come in, we always have to be aware that there could be more than one bug. In fact, typically there is always more than one bug. I like to think of it, there's a major one, and then there's one that's there just to sort of put us off the trail. So in this case, we have this bug superposition. We actually have that noisy image that I showed before, and we have the false colored image. And we have, shall I say, the FPGA has an incorrect configuration of which is the correct start pixel. So when we combine these two, we actually have both vertical noise, we have noise where there shouldn't be any. So in this vertical part here, this is where your optical black would be, and it should be dark. So we have all these weird symptoms. We have this posterization. It's actually hard to see that this is both a color error than just a corrupted data. And so if we take a little bit of time to look at this, it definitely pays to be suspicious that there's more than one thing going on. There are other things that are completely beyond and outside the scope of the actual hardware that we're manufacturing or making. In this case, I took my mobile phone, I took an image with a rolling shutter sensor, and I took an image of my oscilloscope and the old Greytag Macbeth. And what I have, unfortunately, in my office here is LED lights that do not have any ballast. They are not DC driven, they're AC driven. So my lights flicker on and off at 100 hertz because we're 50 hertz power in the UK, and we have a rectified signal, which means we have power twice every cycle. And that means I have 100 hertz illumination flickering on and off. And that gets captured when I put my phone into hardware mode, manual control mode, and change all of the systems. As you can see, the pattern moves as I take different images at a sort of a non-predefined time and space. Just to give you a clear, the camera can do it if I let it do it itself, and it looks quite good. Also, I will say this has AI beautification on it. So these colors look too good to be true. It's because they are too good to be true. But that's the cell phone post-processing. On the subject of horizontal lines, a lot of things that we see are sort of defects within an otherwise perfectly working image. Hey, this camera's working really, really well, but Chris, this line appears every so often, or this line appears and moves as I change exposure. There's a number of different reasons for it. One that the way that I simulated this was I actually enabled a test pattern where I could overwrite one particular line or multiple lines with a black line, and I did that. Now this line isn't black because we're looking through the Bayer pattern. So the Bayer pattern this is how it would work if this was completely black along this pixel, it only means that in this case, a green, let's say green and blue or something like that line was taken out, and it will still take the average values from around it. So it's, you can't say it would be black on the sensor if it wasn't here. So this is why we then look at the raw images. Okay, I think I'm rocking up for the end of the time. Again, this is a huge subject, so I probably haven't covered even a percent of it. But what I wanted to do is just give a quick takeaway slide. And so the first one is the ground up approach. Make sure you are building your investigation on proven steps, and making an assumption at any level, unfortunately, means that if that assumption is wrong, that's wasted time. We have this, clicked a bit too early, but you have the modular approach. Build and test as you go through, just changing an entire configuration and testing it, or copy pasting one and then modifying the parts. That can actually lead to more sort of human error and programmable error. And the last one is register sets are the most common fault. There is no way around this. This is, it's a human. It seems to be a human issue that when something looks like it's hardware, and we all try to work hard and make sure the register sets are right, there'll be an issue. I do it all the time. When I rewrite scripts for these guys and it doesn't work, the first thing I do is think, oh no, I've broken it, and it's a hardware error. But then I would go back and just ratify that my register sets are good. Okay, and that's the end of it. So to me, that felt like 2 minutes. I hope it wasn't too long for you all.
Perfect. Take it from here now, Chris. I want to say thank you so much, Chris, for such a great presentation. And I want to thank everyone who stayed on with us throughout the webinar. It's very insightful, lots of information. Also, just want to let you know, if you haven't submitted your questions yet, please do so by typing them into the questions section, and I'll get to them. We do have a few questions that were sent to me on the back end, so I do want to start by going with those ones first, and when the other ones populate, I'll get to them. So Chris, the first question I have here is in an SLVS-EC based sensor, are there best practices to debug data streams and clocking, given that the clock is generated from the data stream?
Yes, indeed, there is. We have a full sort of path on how we go through it. If I can jump there very quickly, the slide where I presented the numerical investigation of the data within an FPGA, that was actually an SLVS-EC input. So what we would normally do is have you place a sort of a recording block within your FPGA code, put that into your system, and then run it up, and then we can see exactly what's going on here. So we can actually see if your data lines are correctly connected. We can see if they've been correctly configured in the transceiver configuration for the FPGA. So we can actually, just by looking at all the data as it comes into as it comes out of the the receiver side of basically the transceivers of the FPGA, if we have a look at the data there, we can then see, is everything in sync? Is everything correct? We can look for flipped bits. We can do lots of different little options. Typically, we're doing this in conjunction with our SLVS-EC IP core. So we're actually looking at, here's our IP core, here is the transceiver configuration and the sensors communicating through into that. But that division is exactly the same. The data should look exactly the same because it's based on the configuration of your transceiver configuration.
Okay, good answer. The other question that I have is, what is the best way to qualify a contract manufacturer?
Okay, that's a very, very good question, and it is a difficult one. Because I work in the imaging industry, and I have done all my life, the CMs I've been interacting with are typically very good. You know, they're an experienced CM. They work with a camera manufacturer for a while. They have many different camera manufacturers under their, that they manufacture for. And with them, it's all about the communication, making sure that your design for manufacture is compatible with their stuff. If you have a new CM, maybe one that isn't very familiar with imaging, that you do need to look after that relationship and very much focus on their quality control. And image sensor is typically the one of the largest devices that CM will put on a PCB. It's also one of the ones with the lowest temperature requirement, as in you can't boil the sensor, you can't put it at the temperature too high for too long. And what that means is that any kind of issue with the amount of solder that's in there, maybe let's say you've got the reflow machine and one side slightly colder than the other, and that's the side where you'll get lots of failed devices. And that's because the temperature isn't hit. You also have it the other way, where they just unfortunately stick everything through at 220 degrees, and suddenly your image sensors have defects as well as issues due to that heat. So the actual process of qualification is definitely one of, have you done image sensors before? Please build my prototype. So don't just go straight from your prototype with your known good local guys to mass production and with all the changes involved. Definitely get them to run a board of your prototype device to make sure that still works. It also helps get that relationship going as well. I know I'm rambling on this one a little bit, but it is very worrying when you have a CM that doesn't realize that these sensors are very expensive. The guy who's doing the bill of materials and charging you out knows that, but the person on the line doesn't realize that device is actually $1,000 device, for example. And so they can immediately just run everything through, and then they've suddenly got this 100 image sensors on boards that don't work. They all need to have a different amount of solder paste on, but you can't recover that sensor, because reheating that sensor from above to melt the solder underneath to take it off makes that sensor experience a temperature range way beyond its specified temperature.
Okay. Here I have another question. It says, is the sensor evaluation board helpful to diagnose and debug customer implementation?
Okay. So yes, these are very, very useful. Number one, this is a golden reference. For example, I don't have broken hardware in this office. Well, maybe some that I've broken, but I have good working hardware, and this is a reference. And so, especially with the configuration changes, I always use a known working version here, and I try to recreate the issue that a customer may have. So, for example, this is an IMX535. If you're working on an IMX535 or similar sensor, and there was a bug, I'd ask you to send me your register set whilst you go away and do the foundation pin strapping all the way up kind of testing. You can give me your register set, and I can throw that register set at known good hardware. And so and if this has the same behavior that yours does, or similar, because again, I still have an observation issue looking through Sony proprietary hardware, we can then make some estimations and narrow down that problem. I can then also correct your register set in my kind of in this EVB language and send it back to you. But also, if you had that at your side, then you can do that yourself. And typically with these EVBs, you have some good information. This isn't recommended design for most cameras if you check out how big these things are, but it is a good conceptual place to check on power consumption, heat generation, making sure that if a sensor that you have on your system you've desoldered had a problem, you can now stick it in an EVB after some cleaning to make sure that is that hardware still working, aka was the issue with the sensor or was it with the PCB.
Okay. And another part to this question, I guess it's the question number 2, is how much the analog design is relevant for the image quality?
Hugely, especially on the larger sensors, but even on the smallest sensor, any kind of ripple that you have in your analog design, you will see that in your image. So let's say you have a camera that's updating at 1,000 lines per second, and you've got a 500 hertz kind of ripple in your power supply because you may have chosen the wrong LDO. You might have the wrong power PSRR, and that's power supply rejection ratio, i.e., the system can't supply the power at the frequency that you're requesting it, because this column ADC will turn on it. The analog processes will come on and off during time, and then that creates noise. You can also have other circuits you can have ground plane pollution. So, for example, if you have current flowing in one location, you just have this blanket power supply, flood-filled ground plane, you can have many issues. So the analog design is the thing you should focus on. Definitely. And that's a little bit of, if you look back in history, everyone had CCD, so everyone was a whiz with the analog design and taking care of it. Then everything went over to CMOS, and then it became high-speed data connections, and that kind of power supply stuff dropped off. And also we have many more noise sources now inside that that world. Sharing power supplies between main FPGAs, RAMs, and the sensors is something you should not do.
Okay. Another question here is, how do you determine if an error is at the sensor or in the FPGA? How do you isolate the location when you cannot prove it on the hardware?
So it comes down to a you have to build your evidence. So test patterns are fantastic for that. So let's say it's something like the image your system is losing sync with the image sensor. What that means is the FPGA is normally waiting for something to come in at the very beginning, a complex string of bits coming in at the beginning of every line to tell you it's a new line. And then you can say, right, at the end of all these last two zeros, that's when my pixel starts. An error where your FPGA is not catching that, or you're not seeing it, can cause a problem. What is it? Is it the sensor not speaking correctly or not configured correctly, or is it the FPGA? So in my case, I always focus on the image sensor. It's the part that I know the best. Obviously, there's so many different FPGAs out there. I have some familiarity with the Xilinx, but what I can do is I can say, well, I know that doing this with this sensor will create this output. I could then verify it with an oscilloscope or this device here, the internal logic, and then move up that way. It's when you're looking outside in, it's impossible to see. But if you can validate the steps as you go through your design, that's the key to it. I have to say that we use ILAs and internal grabbing stuff much more often than we use oscilloscopes. So, for example, in this office, I think I have a 250 meg scope and I think a same logic analyzer.
Okay.
Which is something like SLVS at 4.5 gigabits. This isn't going to work. Hence, we look at it in this format.
Okay. I have a couple more questions. I'm hoping that we can get to all of them. This is another one that just came into. You use a MapMeth chart to help with debugging color issues. Are there other things that one should look at that will help identify image errors? I think this is a really great question too.
Oh, indeed, yeah. So this is just one of the tools that you would use. And also, unfortunately, it does require a little bit of clarification on what you mean by an error. But let's just say it doesn't perform well. The debayering and color reproduction for a human's consumption doesn't happen on the sensor, at least not on Sony image sensors. There is no Bayer to RGB conversion happening on the vast majority of the sensors. In fact, all the sensors that we sell, but not necessarily all of Sony's. And what that means is that there are processes that are creating the color afterwards. You have to give good information in. So if you have noisy pixels, you're going to have noisy color. So any noise you'd have in the brightness of a pixel will become brightness variation and color variation in your final system, because that noise is the noise in the pixel is used more than once, if you want to think of it that way. So what we would always say is, if you have so if you have the Macbeth, which is good, but if you have multiple different light types, is very, very good as well. So if you have an LED, an incandescent, big, I can't bring it across now, a big fluorescent, something like that. If you bring these different light sources in, they don't necessarily all need to be calibrated, but what they do need to do is offer a different color temperature of light, so you can see the performance of your system. Because you could make it look really, really good under LED light only, because you've tuned it just for LED light, and the system fails when there's an abundance of red light in it, because it typically always amplified that light, because it is, let's call it, the ISP didn't know any better. So that's a good tool if you have access to the ISP tuning tools for any particular device, that is by far and away the best way to do it. You follow their recommendations, and those recommendations are typically using a Macbeth chart, using a controlled lighting and multiple lighting color temperatures, preferably calibrated. You can then generate an ISP configuration for your particular device. Other things to say: try to do it with your complete optical setup. Lenses have color to them. They also add shading in, and they also would, and the shading also affects any kind of denoising that you'd have in your ISP. So test that final system as early as possible.
Okay. I have another one that I think it's a good question as well. It says, can an idle image sensor generate without input power supply, that's in brackets, a voltage in its voltage pins because of the incident light?
I'm not sure I understand that question totally. Could you just say it once more? Sorry.
Can an idle image sensor generate, in brackets, without input power supply, a voltage in its voltage pins because of the incident light?
Okay, understood. So similar to how a solar cell will just basically output voltage if the power's turned on, can that happen with an image sensor? As far as I'm aware, that's not possible, partly because there is no continuous connection to the voltage pins. You could have some, if you think of it, there are electrons being generated and liberated within that system, but the flow is not modeled, and if there is any kind of current flow, that would be through to a ground pin. But that is a very good question, and I haven't had any problems where that was a solution or that was the reason. But whoever that is, if you can give me an email, we can start a conversation about that.
Absolutely. Okay. With that said, I think I'll wrap up the question section. We do have a couple more to get to, but I think we're running low on time. But I do want to say thank you to everyone who stayed on with us. Really appreciate you guys being here. Very, very informative and exciting presentation. I just want to reiterate that we will send you the slide decks. If there are any links, if you do need to speak to Chris directly, please reach out to us and we'll get you his information. Also, the on-demand version of the webinar will be available to you in the next few days. Another thing too, please do follow FRAMOS on LinkedIn and Twitter, where you'll get information, company information, product launches, additional webinars that we might be having in virtual events. Just to let you know, we will be at, oh Lord, what's the name of that event again? Vision, come October this year. So if you're in the position to be there, please check us out and check us at our booth. Thank you so much again. We look forward to speaking to you in the future, and have a great day. Bye-bye.
Thank you very much. Bye-bye.